Okay, so let's look at the centralized solution for the mutual exclusion problem. So here we have a centralized controller that kind of regulates the access request to critical section. So all processes have to communicate with the controller. So a process wishing to execute the critical section sends a request message to the controller, and the controller queues up all these request messages in the order in which they are received. So it's a first in first out basis in the order in which they are received. And so if a process has not yet granted any process the permission to access the critical section, it looks at the request in the front of the queue and sends that process the grant message. So then the process can enter the critical section, and after finishing executing the critical section, the process has to send a release message to the controller. Then the controller will remove the request of the process from its queue and then send out the request grant message to the process whose request has now come to the front of the queue. So a centralized solution is kind of more straightforward, but the main problem with it is that the controller can become a single point of failure. So if the controller fails, we have to go through a leader election algorithm, which is the other model we'll look at after this, again and again to kind of select the new leader. And also the communication channels leading to the controller can become congested, as all these processes have to send the request messages to the controller, and the controller have to send out the grant and the message, and then the other processes send release message, and so on. So a centralized solution is not really preferred, but still there are systems that use a centralized solution if the congestion and the bottleneck issue is not a main concern. Of course, we want distributed solutions. That's what we'll see after this video. Now, just analyzing the performance of the centralized solution, the number of messages that were sent per CS invocation. So basically, for a process to gain control of the CS and then to exit out of the CS and give the permission and let the some other process to enter the critical section, how many messages have to be sent. As you know, a process has to send a request message to the controller, and then the controller, when it wants to give the permission, it sends a grant message, and when a process is done with the critical section, it sends out release message. So it's basically 3 messages per CS invocation, and it is 3 all the time irrespective of the number of processes. So you may have 10 processes or 30 processes, it doesn't matter, you still have to go send 3 messages per CS invocation, only 3 messages. So it does not grow with the number of processes. That's a good thing. So it is a third of 1 complexity, the number of messages, the message complexity. Now in terms of synchronization delay, again, by definition, what is synchronization delay is the time you exit from a critical section, how long it takes for another process to enter critical section. So what happens in the centralized solution is the process exiting the critical section sends out the release message to the controller, and the controller has to then send out a grant message to the other process. So it takes 2 message propagation delays. So if you indicate the propagation delay as t, it is 2 times t. That's the synchronization delay. So a system throughput, which is basically 1 over the synchronization delay plus execution time, is 1 over 2t plus e. Now when it comes to analyzing the correctness of this centralized solution with respect to these 3 properties, the safety property requires us to make sure that only 1 process is executing the critical section at any point of time. And actually a centralized controller does that because it doesn't send out more than 1 grant permission. It sends out the grant permission only to 1 process at any point of time and waits for the process to send a release message. So safety is always guaranteed. The liveness means a process that has made the request to access critical section eventually gets the permission. And remember, the controller queues all the requests to access critical section in the order in which they are received. So if a process has sent the request and the communication channels are reliable, then the request is going to reach the controller and it's going to queue it up, and as the critical sections are executed one after the other by the different processes, the request of this particular process is going to move ahead in the queue and eventually going to come to the front of the queue, and the controller is going to give this process the permission to access the critical section. So liveness is guaranteed. And fairness is also guaranteed because again, the controller gives access to critical section, queues up the requests in the order in which they came. So if one process generated a request and sent to the controller, and some other process generated the request and again sent to the controller. Now again, the controller can, and what is the original assumption of the timestamps of the messages is we could sequentialize or order the messages in according to the timestamps, which means you could say this message was sent earlier than this or after this message was sent. So, and if still two process messages had the same timestamp, we could distinguish them based on the process IDs. So at the controller, if the controller can decide whether one message was sent ahead or earlier than the other message, so it will order the messages in its queue in the order in which they were sent at the different processes. And so a process that generated its CS request earlier would get the permission ahead of another process that generated the CS request later. So fairness is also guaranteed.